Hi, this is Joe Galea, and this is my Pint of Science talk regarding how is the best way to motivate behavioural change in humans. Is it to provide reward, i.e. the carrot, or is it to provide punishment, the stick? And specifically, I'm interested in motor learning, and this is important across our lives, from learning to grasp objects during childhood, to learning to drive cars in adolescence, relearning actions following injury or illness, or even just the simple things during normal adulthood of learning to embrace new technologies such as using a mobile phone. So what do I mean by reward and punishment feedback? Well, imagine you're teaching a child how to play a tennis shot and you want to give a specific bit of information. So for example, shorten your backswing. Now you could provide that in a very neutral scenario, just literally giving the feedback, shorten your backswing. Or you could provide it in a reward context, shorten your backswing. If you get it in next time, then you can get a drink. Alternatively, you can provide it in a punishment context, shorten your backswing. If you don't get it in next time, then you'll be doing sprints. And what I'm interested in, and my research is interested in, is what does providing this feedback in either a reward or punishment context do in terms of how quick the person, child in this example, learns and changes their behaviour, and how long does that memory or that improvement last for. Just give you some funny examples. These are some YouTube videos which give you examples of putting in a reward or punishment scenario. Hopefully you can hear this.
Here comes Dad for a conference. Hey, I just came out to tell you how much I love you. As a dad and a player. Dad, you're doing awesome out here. One more hitter and then I'm going to juice. This is your last hitter. Okay? You understand? Come right after. Hey, cheer up. Have some fun. Come right after.
Okay, so this is a parent being extremely positive, providing feedback, putting in a reward context. Now this is the opposite.
Pee-wee football for 8 to 10-year-olds. And for the most part, the parents on the Jupiter side of the field, while boisterous, were under control. But on the other side of the field,
You need to stay with me and act like you want to play this game. No, you're not. And you're not. You're moping around, going, how come I'm not getting to play?
this is the visiting team from another town up the Florida coast. On this side of the field, the atmosphere is a little more, well, let's call it intense.
Oh, I guess they got that one too, huh? Yeah, they'll get them all, I'm sure. Hey! What is that? Come on, Tyler!
Okay, in this scenario you can clearly see it's in a punishment context. And these are kind of, I imagine it, very extreme examples, but this is the kind of thing where I'm interested in. What does this do to how people learn and how much they remember? And this all comes from classic psychology experiments. Firstly, Thorndike in the 1800s, but then Skinner in 1948 really kind of operationalized this kind of learning. It's known as operant conditioning. Basically, it's a changing of behaviour by the use of reinforcement, and there's positive reinforcers, which increase the probability of a behaviour being repeated, and there's negative reinforcers or punishers, which decrease the likelihood of a behaviour being repeated. And the way Skinner looked at this is through putting a rat in a box, and it's called Skinner's box. And initially, the rat would walk around the box, no idea what to do, would be pressing random things, just trying out different actions, and then all of a sudden they would find the lever. The lever would enable food to be released, and this would kind of be the eureka moment where the lever would be associated through operant conditioning with the reward, and therefore the rat would learn this behaviour and continue repeatedly doing it because they want to get the reward of getting food. Now you can also look at things like punishment in this scenario by when the lever is pressed, the floor will electrocute the rat. What this will do is it will stop this behaviour being performed. And it gets even more complicated than this. So there isn't just reinforcement and punishment, but there's also even more detail when you go underneath these two. So you've got reinforcement, which increases behaviour, punishment, which decreases behaviour. But within reinforcement, you've got positive reinforcement, so giving a treat when the dog sits. But you've also got negative reinforcement. And this goes into two different scenarios. One where it's called active avoidance, so studying to avoid getting a bad grade. And then escape, turning off an alarm clock by pressing the snooze button. Okay? And all these things are increasing this behaviour. Alternatively, you've got positive punishment. So this is spanking a child for cursing. Very bad example now, because I know you're not allowed to do that. And then you've also got negative punishment. So telling the child to go to his room for cursing. So you're removing the positive thing to stop that behaviour from happening. So it kind of gets a little bit, so it does get relatively complicated, and there isn't just the simple reward and punishment. Now, interestingly, it even gets even more complicated, because even within, for example, reward, you've got intrinsic and extrinsic reward. Intrinsic reward are kind of the internal things which make you like and enjoy doing particular actions. So it's kind of an internal drive, feelings from within, enjoyment of the performance, satisfaction of performing, pride and well-being. These are kind of intrinsic reasons why, intrinsic reinforcement why you perform particular actions. Then you've got extrinsic, which are kind of like giving points, giving praise, getting money. And what's interesting is it's been shown firstly that these two things can conflict with each other. So if you provide extrinsic reward, this can reduce the intrinsic reward and stop people performing actions when you don't provide the extrinsic reward anymore. So extrinsic reward can be beneficial, but it can also be negative as well. And I just want to give you an example of this. And although this isn't to do with motor learning, it's a good example of when extrinsic reward can be a negative side effect, can produce negative side effects. So this is a really famous psychology experiment by Dunker and Glucksberg, and it's called the candle problem. And I just want you to look at this, and basically what you've got to do is attach the candle to the wall and burn it without candle wax getting onto the table. Now what usually people do, and I'll let you have a little bit think about this, but what people usually do is they'll think, well, maybe I could pin the candle to the wall. That doesn't work. Maybe I could use the matches to melt the candle and stick it to the wall. That doesn't work because they always start to melt. And what actually you should be doing is using the box. So if you empty the box from the pins and then use the pins to attach it to the wall, it becomes a candle holder. And you can then easily melt your candle without it hitting the wall. Now, what's interesting is when they had two groups in this situation, and in one situation they were just try as fast as you can to solve this problem, and in the other one you gave them a reward and said, based on your time, if you get in the top 25%, then you get a certain amount of money, and it's a relatively large amount of money for the time. So what you would predict is that the reward group would learn a lot faster than the non-rewarded group. But what was actually found was the complete opposite. So the reward group, every single participant reacted slower, took longer to work out this problem than the non-rewarded group. However, if you took the pins out and gave them the box, so it becomes a lot clearer as to what you should do, the reward group in this scenario did significantly better. And what it's been suggested is that what reward does is it allows you to focus on a particular problem. However, and so this is good for very simple menial tasks because it focuses you on that problem, it allows you to kind of really think about that, but it doesn't allow you to be open, it doesn't allow you to think about different logistical issues. And so the thought is in complex problems, giving reward may be bad because it stops you having an open mind. But in simple scenarios, extrinsic reward may be good. Okay, so back to sport. So how do we examine motor? So what I want to talk about are some studies which we've done in our lab about how people, the effects of reward and punishment on motor learning. The first question is, how do we look at motor learning in the lab? And what we usually look at is a thing called motor adaptation. And this is an example of motor learning where people adapt actions that have already been learned to new scenarios, new environments. So for example, if you've learned to play tennis on grass and then are going to play on clay or hard court, you don't relearn your tennis shots, but you adapt them for the new environment. For example, with the different bouncers, the different size of the bouncers on these different courts. So I just want to give a quick volunteer, and actually in the Pint of Science talk I will be showing people visual adaptations, so giving people prism glasses, getting them to throw balls at a particular target, applying the prism glasses, showing a big error, and then showing how people learn to adapt to that. It's just an easy motor adaptation task. Actually in the lab, this is how we look at it. So we get people to make reaching movements. They can't see the hand, but they can see a cursor on the screen, and the hand movement controls that cursor. During baseline, we just get them to reach towards a target. We then introduce a visual displacement. So when the hand moves towards a target, the cursor on the screen moves 30 degrees to the right, so clockwise. And to adapt to this, they have to move 30 degrees counterclockwise. And that's called adaptation. So the rate at which they learn to adapt to that visual displacement. And then what we do is we remove vision and we see how long they continue to move in that altered direction even though there's no need to. And that's a measure of retention, or the memory of this new sensory motor memory. And to the scenario, what we did is we added reward and punishment. So if they hit the target, in the reward context they got 4 points, and then the further they're away, 3, 2, 1, 0, and this was related to gaining money. And then in the punishment context, if they hit the target, they didn't lose any points. The further they're away, the more points they lost. And this is related to losing money. And what we're interested in is how this reward and punishment during adaptation influenced the rate at which people learn and the amount that people remembered. And this is just the three groups. We had neutral, reward and punishment. And remember, they were adapting to a 30-degree displacement. So they needed to produce a reach direction of 30 degrees. So the faster they get up to this point here, the greater the amount of learning, the faster the learning there is, the better the learning there is. And what we found was that punishment caused a greater and faster amount of learning in comparison to reward neutral. So our conclusion was that punishment caused faster learning. However, then when we looked at retention, what we found is the complete opposite. So punishment now looked like neutral, and reward, so the reward memory is better retention, so how long they continue to move in this altered direction. Reward caused a greater amount of retention. So we get this clear dissociation where punishment caused faster learning and reward caused greater retention. Why do we think this? Well, our conclusions in the paper was that maybe reward and punishment are different chemicals in the brain are important for these two effects. And what it's been suggested, not in motor learning but in other fields, that reward is related to dopamine and punishment is related to serotonin. And what's interesting is within this motor learning task, the adaptation or learning component occurs at the back of the brain, here the cerebellum, but then the memory part is stored in the front of the brain. And when you look at where the dopamine and serotonin is in the brain, you get lots of dopamine in the front of the brain and lots of serotonin in the back of the brain. So our conclusion, even though we don't have a huge amount of evidence for this at the moment, is that maybe serotonin is important for the learning component, and that's why punishment is improving that. Maybe reward and dopamine is important for the memory component, and that's why reward is enhancing that. One of the things which we have found though is that not everyone is as good or as sensitive to these kinds of feedback. So you get some people who are really sensitive to reward and punishment and other people who don't. And just an example of this is a slightly different task, but what I want to show you is again keep maintaining, staying in this grey area is shown perfect learning, okay, motor learning. And what we found is when we tested 30 people, and this is just for a reward task, when we give people a reward, we get this kind of separation. So we find that 2/3 of people, so 66% of people, are able to learn this task perfectly. So they're sensitive to reward, they can use a reward and learn this task perfectly. However, 33% of participants, and these are young, healthy participants, completely failed on this task. And so we get this clear dissociation in young, healthy participants. And what we're interested in now in the lab is, can we try to understand why within the young, healthy population you have a group of people that are really successful and a group of people that fail completely. And so now we're collecting data in over 300 participants, and what we're looking at is whether people's genetics are important for how sensitive and how good you are at using reward to learn new actions. And our prediction is that dependent on the genes which are important for the amount of dopamine in your brain will predict whether you are a good or bad learner. So that's kind of where we're going and what we're looking at. And so to kind of just finish up on this, the last question is, well, why is this important? And the reason why we think this is important is because of the lack of research which has been done in terms of the importance of reward and punishment in things like stroke rehabilitation. Now, stroke rehabilitation involves learning, relearning actions, relearning motor behaviours, because you've had a stroke and now your arm or your leg is not working as it used to, so you've got to relearn these actions. And what it's been found, so we've done a study, but also this study done in 2014, they were trying to induce some rehabilitation in the ankle, so to produce greater flexibility in the ankle. And what they showed is, if you had provided the feedback on a computer screen, and in one group you gave them lots of reward, lots of kind of extrinsic reward, and compared that with a group that that got minimal amounts of reward, you get a clear difference in terms of their improvements. So this is one patient who didn't have any reward, and this is basically showing that there's very little difference between pre and post training. However, in the reward group, you've got these some participants or patients that showed a huge improvement from pre to post. And what their conclusions was that the reward increased or enhanced motor control and motor learning in these patients. And so putting this together, one problem though is that not all patients are as sensitive as others. And so what we're interested in is, can we predict whether patients are going to be, and people are going to be sensitive to reward and punishment? Are they going to be more sensitive to reward or more sensitive to punishment? And can we then develop bespoke rehabilitation interventions which determine which groups patients should be in? So if they've got increased sensitivity to reward, we put them in a reward group. Increased sensitivity to punishment, put them in the punishment group. If they're not going to be sensitive to either, maybe we should put them in a neutral feedback group. And to show kind of how this is being developed also, and how this is kind of a state-of-the-art question, is there's actually clinical trials now going on looking at, does motivation matter in stroke rehabilitation? So hopefully I've kind of shown a little bit of information regarding the importance of reward and punishment in motor learning, how they can have differential effects, but also that people's sensitivity to reward and punishment isn't consistent. And our goal going forward is trying to understand why certain people have different sensitivities. So I want to finish by acknowledging people in my lab that did this work, and also people at University College London who were involved in this work, and my funding body. Thank you very much.